Now, what about the other coefficient? The other coefficient. So if we fix C1, so if we fix 5 and we want to change the profit of chair, then this becomes C2, right? So again, it is negative C1 over C2, and now C1 is 5. So what we want to then say is negative 5 over C2. Okay, negative 5 over C2. And C2 is a positive number for now, so it's easier. Okay. Again, the bounds are the same because we have to be greater equal to minus infinity and less than equal to minus 3 over 4. Okay. Here, there's a little bit of a trick here because trickiness here, because if we allow C2 to be negative, then or even 0, then we'll have some problem. So just assume that C2 is greater than 0 for now. Again, we split, right? Negative infinity less than equal to negative 5 over C2. Negative 5 over C2 less than equal to negative 3 over 4. Okay. Now we multiply by minus 1 to get rid of them. We get 5 over C2, change sign, yeah, 3 over 4. Then we don't want C2 to be at the denominator. Because C2 is positive, so we don't change sign again. We can just multiply by C2, cancel, cancel. So 5 greater equal to 3C2 over 4. And then we can get rid of the 3 and the 4 by multiplying 4 divided by 3. So 20 divided by 3 less than equal to C2. So C2 cannot be larger than this. Now we multiply both sides by negative 1, 5 over C2. Okay. And that's a little bit of a problem. So what we do is we need to multiply by C2. We need to take reciprocal. Now, suppose we say 5 is greater equal to 3, right? If we take reciprocal, 1 over, then we find that it is 1 over 3 is now in turn larger and greater than equal to. So we can invert when we do reciprocal, we need to change sign again. Oh no, I wrote wrong. So this should be greater equal to, because I multiply by minus 1, I change sign, but now I change it back. So I take reciprocal, C2 over 5, and then 1 over infinity basically says 0, less than equals to C2 over 5, but I can multiply by 5. 5 times 0 is 0, so that's all. In other words, C2 better be greater equal to 0. That's our assumption anyway, but it cannot be too large. Too large means less than equal to 20 over 3, roughly 6.67, nearly 7. And that's the kind of maximum amount that we can increase in profit. So from $2 to $6.60, 67 cents, and that's the maximum without changing 8,3. All right, so that's basically how we are going to find out the allowable change in the objective coefficients. Okay, so now let's get back to our our screen, and I've taken the liberty to just run the Excel. So if we do the Excel, right, and if we just ignore this for now, we will set it up in this way, right? The some product x1 is less than equal to 8, x2 is less than equal to 6, 3x1 plus 4x2 less than equal to 36, x1 plus x2 greater equal to 1. So everything is nice and proper. Then we solve for it by selecting objective function, changing variables b2, c2, less than, less than, less than, greater than, equal to, simplex LP, and so on. So the standard stuff. And then when we solve, okay, we found that the solution is 8, 3 with a maximum profit of 46, exactly as what we have found using the manual graphical approach. More interestingly, if we run sensitivity analysis and look at, all right, the outcomes, you find that the sensitivity report will tell us the allowable increase and decrease of each coefficient while holding the other coefficients fixed. Right now, we only have one other coefficient, right? We have a two variable LP model problem. So in the case of $5 per table, we ask the question, to what extent can we change the 5 so that 8, 3 remains an optimal solution? Well, according to our analysis just now, C1, which is this 5, right, cannot be more than infinity. Well, that's Excel's way of saying 10 to the power of 30, infinity, right? And it cannot be less than 1.5 as what we found just now. Okay, which means that 5 minus 3.5 is 1.5. And so the allowable reduction, or decrease is by the extent of 3.5. So 5 minus 1.5 is 3.5. Likewise, when we look at our C2 analysis just now, to what extent can we change the coefficient 2 so that 8, 3 remains as optimal solution? We found that the minimum range was 0, maximum was 20/3, right? So we can reduce 2 down by maximum of 2 so that it is at least 0, and increase 2 by a maximum of 4.667, which is like adding up to 6.6667, which is basically 20/3. And so now you can see the link between how Excel gets all these allowable increase and decrease by essentially tilting the objective function line about the optimal solution this way, right? So of course, in a 2D scenario, two variable situation, we can see the one-to-one correspondence, and we can actually do the analysis ourselves. But number one, we won't do that even for 2D because it's a slow process. And fortunately, I didn't make any mistake here. But if we do this many times enough, I'm sure one of those situations I'll make some careless mistakes, which is very unnecessary because we can always use Excel, right? And number two, and more importantly, in commercial real life situations, we tend to have a lot more decision variables. So our sensitivity report can have 200 rows because we have 200 decision variables, and we are no longer able to individually calculate all the allowable increase and decrease easily or at all, actually. Yeah? So we'll make use of software packages like Excel Solver or Python R to solve these problems. But nevertheless, I hope you have gotten a great insight into how Solver thinks about finding out the allowable increase and decrease. And there's nothing mysterious about what Solver knows that you didn't know or you cannot know. It's all there, right? It's all very visual. So let's come back to our screen here. And essentially, then we are done with finding the bounds of objective coefficients. See you in the next section.